Hello everyone, welcome to lecture 47 and the course Diffusion in Solids. So today we will be talking about the diffusion in nanocrystalline materials. So you all know that in nanocrystalline materials, these are very important nowadays. Nanotechnology, nanoscience is one of the major interest research-wise as well as technological applications are immense. And nanocrystalline materials are predominantly characterized by a very high fraction of grain boundaries. And we already saw when we were talking about the grain boundary diffusion that grain boundary acts as a faster diffusion path. So that influences, and that's why it is a good idea to consider these diffusion aspects in nanocrystalline materials separately. Although you will see that we will be talking about polycrystalline or the kinetic regimes of diffusion in polycrystalline materials going from a coarse grain size to very fine grain size. So these are the concepts that we will cover, and these are some of the keywords. Very simple schematic. This is how a coarse grain structure looks like. This is how a fine grain structure will look like, or a nanocrystalline structure with the grains are in nano. Of course, there is no micron here because micron marker here, because the intention was only to show a schematic that these are the fairly large grains, these are fairly small grains. Now, when you have a micro crystalline material broken down into the nanocrystalline grains, what is actually happening is a large increase in the surface area to volume ratio. For example, you consider this cube which is of unit edge length 1 meter. So the volume of the cube is 1 meter cube, and the area, the total surface area, if you look, it is 6 into 1 meter square, which is 6 meter square. Now let's say I break it down into four cubes or equal dimensions. Then what I have is that the volume remains same. So the edge length will become half, and the number of cubes that I can cut here. So I cut into 8 cubes actually. So 8 into 6 into 1 by 2 whole square gives me 12 meters square. So you already see that the surface area is increased. Suppose I break it down into 27 equal cubes, where each will have a edge length of 1 by 3. Now the volume still remains same, but if I calculate the surface area, it becomes 6 into 1 by 3 whole square into 27, which is 18 meters square. So you can see just by breaking into from one single cube to only 27 pieces of edge 1 by 3, then the area changes to 18 meters square. It becomes 3 times. Suppose I cut it in such a way that the edge length, instead of changing from 1 to 1 by 2 or 1 by 3, now I break it down into cubes which are 0.1 millimeter edge length. Okay, 0.1 millimeter edge length. So that is very extremely small, and that if you try to calculate the area, you will get a very large number, which comes out to be 14.8 acres. So that is how much you will see that the increase in the surface area to volume ratio can occur. So this is how the influence of, when you go to nano, the surface area that you have is so high. And you know that when you talk about the surfaces are the reactive centers, and therefore the properties of the nanomaterials become distinctly different from their coarse grain counterparts. Now, as I said, that the field of nanocrystalline materials has progressed significantly, and therefore now people are able to synthesize nanomaterials through a variety of methods. One of the classification is physical methods, chemical methods, and biological methods. So where people even use plants, microbes to make nanomaterials. Among the chemical methods, sol gel, chemical vapor deposition, colloidal, spray pyrolysis, these are the popular methods to produce nanomaterials. Physically also, you can go for a mechanical method. Mechanical method means that you have the coarse grain structure, and you now apply stresses or the supply energy to break it down to the nanometer grain size. So you have high pressure torsion, ECAP, these are the two popular techniques. There are others as well. Then you do mechanical milling. So these are the high energy ball milling techniques with which you can make the nanocrystalline materials at the room temperature. Vapor method involves physical vapor deposition, sputtering, laser ablation, laser pyrolysis, and so on. So there are host of synthesis methods available to produce these nanomaterials. Now, diffusion in polycrystals and nanocrystals. To understand that, again, we understand it in terms of the kinetic regimes. So, depending upon the relation between the diffusion depths and along the grain boundaries, along the length and so on, and how it compares to the grain size, kinetic regimes are defined. And in addition, in nanocrystalline materials, diffusivities are affected by structural relaxation, grain growth, residual porosity, and different types of interfaces and triple junctions. All these are the for example, triple junctions are the defects which can contribute to diffusion. When you synthesize nanomaterials, there can be residual porosity, which provides another type of, you can say, a medium for the diffusion to occur. And grain growth, that means if grains are growing, then also the diffusivities are affected and so on. Just to give you another feel that if you have a 10 nanometer grains, for example, the 20% atoms lies in the boundaries, whereas if you have 5 nanometer grains, approximately 50% atoms lies in boundaries. So you can see that the grain boundary diffusion attains so much of importance. For example, if you consider the grain boundary diffusion of copper at 700 Kelvin, let's say, for 1 minute, let's say for 1 minute if it is annealed, then the root DGBT comes approximately equal to 8 microns. At room temperature, the root DGBT comes to 1 nanometer. Now, this 1 nanometer, if it was a coarse grain copper structure, you can say, okay, this is nothing. But if the copper is nanostructured, that means if the grain size itself is 5 nanometers, 10 nanometers, then this 1 nanometer diffusion is also significant. So, therefore, the grain boundary diffusion becomes comparable even at room temperatures when you talk about the nanostructured solids. Now, what happens is that we talked about, let's say, the kinetic regimes of diffusion when we were talking about the grain boundary diffusion. Although we understood that, yes, the grain boundary diffusion, because the grain boundaries, the sizes can change as a function of time. So, there is a certain kind of a time dependence that may be involved. But that is even more prominent when you talk about the finer structures or, ultra fine structures or the nanostructure, because they have a higher propensity for the microstructure to evolve. Because when you synthesize nanomaterials, many times the structure, the nanostructure is a metastable structure, or it has a high propensity to decrease its energy through the grain growth and certain relaxation phenomena. So, therefore, depending upon the grain size and depending upon the temperature, how much is the diffusion length, there are additional kinetic regimes that have been defined. And these kinetic regimes evolve as the annealing times increase, as you heat a particular nanocrystalline material for a certain duration, then the kinetic regimes also change. And this was studied in detail by the group of authors Kaur, Mishin and Gust, which is summarized in this very nicely written text here, for which the references are given. So, the schematic of these regimes are shown here. This is a C kinetic regime where we have seen, for example, this applies when you have LB and D and LGB in this kind of a relation. What is LB? LB is the lattice or the bulk diffusion length, which is equal to root dt. LGBB is equal to the effective grain boundary diffusion length in the B kinetic regime, which is given by root S dGB delta divided by 4 d power 1 by 4 into t to the power 1 by 4. LGB C is equal to root DGB T diffusion length inside grain boundaries in the C region. Now, there are certain schematics for C and C dash. Then there is, so for example, if you see C and C dash, the diffusion is happening in the grain boundaries only. You don't see a bulk diffusion here. But now the grain boundary, so here the fraction of grain boundaries or the grain size is slightly higher than this. Lower than this. So then you have similarly a B2 regime, you have a B2 dash regime, you have a B4 regime, and then different types of A regimes also. So we will see this as we go along now. And this was the which regimes will be operative, which regimes will evolve. It depends upon the type of the polycrystal that we are dealing with. So this was summarized by in this reference. So for the coarse grain, this is the sequence of diffusion regimes in time. In time means that if you take a material and do the diffusion annealing at a particular temperature, as the time increases, the kinetic regime changes from one to another, and that is the sequence that is given. So C to B2 to B4 to A for the coarse grain structure. For the fine grain structure, it is C to B2 to B2 dash and A dash. For ultra fine grain, C, C dash, B2 dash, A dash, and in the special ultra fine grain, B is not there, C to C dash and A naught. We will see now this in more detail in the upcoming slides. So, for example, the coarse grain, if you take the coarse grain, what we mean is that the D is very greater than the L double dash. What is L double dash? I will define very shortly. So, D is the grain size. So, this as I said that we are trying to understand the evolution of the kinetic regimes as a function of time. So, in this direction we will be keeping the increasing time. So, let us say we start with the C regime. So, C regime means you do not have a leakage flux. The grain boundary diffusivity is much higher than the lattice diffusivity D, which also means that the characteristic grain boundary length in the C regime is much greater than the bulk diffusion length, which is LB. LB is nothing but root dt. This also implies alpha is greater than 1, which we have already seen, and the LB, that is the bulk diffusion length, is less than S delta by 2. That means LB is very small, so you can neglect it. And in this regime, you can directly determine the DGB. And this characteristic length LGBC is directly proportional to root T. So, remember LGBC represents the length here. So, the diffusion length here, it is proportional to root T. It is basically like root DGB T dependence. So, root T it is proportional to. Now, with the increasing time, this changes to a B2 regime. So, that means if you keep because the time increases. Now, what has happened, what happens is that LB becomes greater than S delta by 2. So, this inequality has changed. If you see here, this inequality has changed. As you increase the time, the more and more bulk diffusion can happen, and LB becomes greater than S delta by 2. It still is less than LGB, and still LGB is less than D. So, you see two slopes in diffusion profile now, and the penetration depth of grain boundary fringes is LGBB, and the triple product can be determined from the grain boundary diffusion TEL. And this length GBB which we have defined previously is proportional to T to the power 1 by 4. Remember, in the C kinetic regime, it was proportional to root T. Here it is proportional to T to the power 1 by 4. When, at what time this transition happens, it can be written by equating this. LGBC is equal to LGBB, which will give you the transition time as D dash equal to S square delta square by 4D, and L dash is equal to S delta by 2 root DGB by D. As you increase the time further, now what happens is here the LB was very less than LGB, but as the time increases, the LB increases much faster than LGB till a point is reached where LB is almost comparable to LGB. So here you have a nearly planar front and Gaussian or error function type of solution is applicable. So here the transition time is again obtained by equating LB equal to LGBB, and here T double dash is the transition time is written as S delta DGB whole square by 4D cube, and this is the L double dash which is S delta DGB by 2D. So this is the L double dash which we defined here. So if the grain size is larger than this length, then this is the kinetic, these are the what you describe as the coarse grain material. That means you can say that D is the maximum than all the other characteristic diffusion lengths. And finally, the A kinetic regime kicks in when this LGB and LB become even larger than the grain size. So when they become very large than the grain size, this A regime is reached, where the effective diffusivity is dominated by the lattice diffusivity. Now let's see the regimes for fine grained structure. So fine grain means that the D is between L dash and L double dash. L dash, remember, is a transition between C to B2, which we defined before. So if you see this figure, L dash is given by this parameter and L double dash is this. So if the grain size lies between these two, again if you see with the evolution, so the C kinetic regime, this is same as the case before, and again as the time evolves, the first regime to kick in is B2, and here the transition times are same as was given in the case of coarse grained slide. Now here there is a small change that occurs. Instead of going to from B2 to B4, it goes to B2 to B2 dash. So here the tracer penetrates far beyond the average grain size, and this condition you see that here the LGB was less than D, but as the time progresses, the D becomes less than LGB. So the tracer penetrates much more than the average grain size. Still, the grain boundary fringes do not overlap, and the Fisher model is applicable if we use a effective grain boundary width, which is written as G by A, where G is the geometric factor and A is the grain boundary area per unit volume. Okay. So this you can see also how in the previous slide, if you see how it is different from B4. B4 the grain size is much larger. So now here, because the grain size is much finer, then you don't really get to B4 regime, but a regime called as B2 prime, okay, which is like the slight extension of this. So the transition times now can be calculated again, and T double dash is S delta DGB whole square by 4D cube, and L double dash is S delta DGB by 2D. Okay. So here this is also calculated by LB equal to LBGB. Now again this if you increase the time further, you enter a dash regime. Here, because now the grain size is finer, the effective diffusivity is dominated by the grain boundary diffusivity. So A prime and A naught also we will see all are variants of A kinetic regime. The symbols are used just to indicate that when we say A prime, we are talking about a fine grain polycrystalline material. When we talk about A, it is a coarse grain polycrystalline material. When we talk about A naught, as we will see, it is another class of material. Now, when you talk about ultra fine grain, that is D is much less than even L dash, then initially you have a C kinetic regime, this remains same. Then what happens is because of the finer structures here for times longer than a certain transition time T dash, the diffusion process reaches the C dash regime. So this happens at the transition time T naught, which is given by D square by DGB. So basically this happens when D is equal to LGB C. So, the finer, very fine grain size, again here the tracer penetration is much larger than the grain size. So, here, but there is the bulk diffusivity is still small. So, therefore, you see this is the written as C dash instead of a B regime kicking in. So, this gives us the transition time d by L dash whole square into T dash. Then again, as we increase further the time, the B2 dash regime kicks in because it is ultra fine grain structure. So, again tracer penetrates far beyond the average grain size, and effective grain boundary width can be used to apply the Fisher model. And after that, then A dash regime again comes in, where the effective diffusivity is dominated by the grain boundary diffusivity. So, the special case are the ones where now, so far, although the S is there, but S value is very close to unity. So, the role of S is not so prominent when we consider these previous three cases. But there are regimes where or there are materials in which the ultra fine grain structure is there, and then strongly segregating solutes are present. So, that is why the S plays a certain role here. So, in that case, when the D is much less than S delta by 2, the first regime is the C regime. Again, it remains very similar to what we have seen before. Then, for the times which are longer than T dash, this changes to the C dash regime. And this again, the transition times are similar to what we saw previously. But now, the change is because of these strongly segregating solutes, there is no B regime that is attained directly. What happens is the A regime is attained, it is referred to as A naught, indicating that we are talking about ultra fine grain structures with very strongly segregating solutes. So, in this case, there is no B regime that enters, it directly goes to the A regime. The effective diffusivity is given by modified Hart-Mortlock equation, which we'll not be discussing, but here the effective diffusivity is not given simply by GD plus 1 minus GD GB or the combinations like this. Now, because in the ultra fine grain or the nanocrystalline material, there are a lot of grain boundaries and grains, lot of grain boundaries is comparable to the grains that are present. So, effective diffusivities are written based on the direction or based on the arrangement of the grain boundaries and the grains. So, for the case LB greater than root dt, you have where the grains are arranged or grain boundaries are parallel slabs, then the effective diffusivity is given by the Hart equation G d G b plus 1 minus G into D, where it is arranged like this in the series, so to say. In that case, the effective is given by dGb into D divided by G dGb plus 1 minus G into D. And if they are arranged in this manner, where let us say these are cubes, and then in that case Maxwell had come up with the equation like this. He proposed this equation dGb into 3 minus 2 dG into D plus 2G into dGb divided by G dGb plus 3 minus G into. The solute diffusion equation also can be described for each of these combination. So, these are the equation given here. So, you can see these are the segregating factors that come into picture, and here these are the Maxwell equation is also modified taking into account the solute diffusion. So, with this we end the discussion on the nanocrystalline materials diffusion, and we will talk about quasicrystals in the next lecture. Thank you.